Welcome back. Today we're going to conclude probably with divide and conquer strategies and algorithms, and then start on the next topic, which is related to trees and tree-based data structures and tree-based algorithms. Which hopefully you've gotten a lot of that already from, say, computer science too. But we'll cover one very specific thing today, which will be the last thing that you will need for assignment 2, which is, of course, programming heavy. There are no written questions for assignment 2, I believe, but don't quote me on that. Okay. So remember that we are live on Piazza here, and if you have any questions, go ahead and post there. I'm also, of course, monitoring the YouTube comments. Okay. What I wanted to do first, as our last thing for divide and conquer, is revisit the problem that we started this course out with. One of the problem that we started out with was the closest pair of points, and I've got the Python code that we developed for that. And we can take a look at that again. And this is the naive approach. This is the brute force approach. So again, the situation is you've got a bunch of points in the Euclidean plane, points being x and y coordinates. What the initial solution that we came up with was, well, let's go ahead and set this minimum distance to be very, very high, so that the distance between any 2 points is, of course, going to be less than infinity. And then what we ended up doing is we ended up generating every single possible pair. These are index values here for I running from 0 implicitly up to n minus 1, minus 1, so minus 2 inclusive. For j running for I plus 1 up to n. Why did we do that? Because we don't want to, a and b and a, they give us the same distance. So we don't want to compute that twice. And that's why if we're looking at point I, then we don't look at all the points before it. Instead, we look at all the points forward in the list or the array or however you're storing these things. And then we just made a nice get distance function over here. Again, it's going to be Euclidean distance is measured by the L2 norm, whatever it is, the square root of the squares of the differences of their coordinates. So x1 minus x2 squared plus y1 minus y2 squared, and then you take the sum of those two things, and then you take the square root of all that. I had a convenience function here to generate a bunch of random points between x values and y values of negative 1,000 up to 1,000. And once we ran over every single possible pair and got their distance, we just kept track of what's the minimum distance so far. And then we output that. And you can see that working here. All right, very, very quick for 100 points. I generate 100 random points. I'm timing myself here and timing how long it took me to do that. But you can see that if we go up by an order of magnitude here, 1,000, it's going to take about 100 times as much time. Because this is an order n squared algorithm. For every single point, that's going to be that's n choose 2, that's going to be order n squared. All right, we're generating combinations, combinatorial objects. And even though k is 2 in that case, it's still, quadratic. And so any increase in the input size, we go from 100 to 1,000. That's 10 times as big of an input. Because it's order n squared, that means it's going to be 10 squared, 100 times slower than it was before. And we've observed that right here. Before it took 0.008 seconds. Let's go ahead and just round that up, 0.009 seconds. And so 100 times slower is going to be almost 1 full second to do that. If we go up to 10,000, it gets even worse, right? Now there are constant factors out front that affect this, and obviously I'm running other stuff on my computer as well, so it's not going to be an exact. But if you took like an average of this stuff, you would see a quadratic kind of behavior if you graphed it all out. 100 times slower here is of course going to be about 2 minutes, so we'll go ahead and let that run. What I want to do instead is I want to look at a divide and conquer kind of approach to this. We're going to start out with a naive way of looking at it, even with that divide and conquer. Still hasn't run yet, so let's go ahead and transition over here. We'll come back to that and see how long it took. So here's the idea of that I want to divide. So suppose that I've got a whole bunch of points. Let me make this thicker. There we go. All right, you know, I've got a whole bunch of points here in the Euclidean plane. It's all over, right? My divide and conquer approach is going to be as follows. We'll divide it by drawing a line right down the middle, right? And we'll call this the left partition and this one the right partition. And then we'll recurse. And we'll say, well, go ahead and find all the closest pairs in the left partition. Go ahead and find all the closest pairs in the right partition. And suppose that you find that these two are the closest pair over here in the left, and that these two are the closest pair over here in the right, right? And they have a distance of delta 1 and delta 2, respectively, right? So, again, what I'm doing here is 1, divide points into two roughly equal sets, equally sized sets, right? 2, recursively conquer, find the closest pair in each set. Or actually, I'm gonna call them what they are. They're partitions. I'm partitioning it into a left partition and a right partition. 3, take the closest between the two distances. Right? So if I've got D1 and D2 here, then my minimum distance overall is simply just the minimum of delta 1 and delta 2, right? And that's easy enough, right? So that's the divide and conquer approach. Now, you got to also keep in mind that we are doing this recursively. So where do we stop, right? You stop when the partition only has 2 points. Right? Now, it's not going to be evenly divisible, right? We've seen this before with binary search, merge sort, whatever, that you could have an array of odd size, 11 elements. And you want to, in merge sort, you want to split it up into 2 subarrays. One of them is going to necessarily have 5 elements, and one of them is necessarily going to have 6 elements. So it's not always going to be an even split here. And because we might not have an even split when we do this this recursion, we can actually set a different base case strategy, right? When the size is small enough. And I'll let you decide what's small enough. Well, small enough is 2, right? If you have a set of size 1, there is no minimum distance because you can't say it's 0. Then that would be like a trivial solution. You could say that small enough is 3. And then you would compute, 1, 2, 3 possible distances and then take the minimum among those 3. You could decide that, well, like a hybrid merge sort, kind of, you could say that, well, once we get down to a small enough number of points, we'll go ahead and switch over to that brute force strategy that we developed before. Right? That could be 100 points, because as we've already observed, and now it has stopped, so I'll transition back over here. As we've already observed, when you've only got, say, 100 points, right, it takes a minuscule amount of time. Whereas if you were to do it recursively all the way down, 100 points all the way down to just 2 points, you end up paying for that recursion. So what you could do is, instead of going all the way down to a set of size 2 and then worrying about, am I dividing it in half correctly? What do I do when I only have 1 point? What do I do when I only have 0 points, etc.? You can go ahead and forget all that and just say, well, my cutoff point is going to be, say, 100 points. When we get down to 100 or fewer points, then we'll go ahead and use this brute force algorithm over here because it's not that bad. Right? In fact, it might be better because you're not paying for the recursion and you're not paying for the splitting of the partition, find the minimum among those 2, right? You just go ahead and get it done. That's how the hybrid merge sort kind of works. That merge sort, you split it out into two sets, two roughly equal halves of an array. And then, as it's presented, when you get down to just one element, by definition, that's sorted. You don't have to go all that way. You could say that when your array is small enough, we'll go ahead and search over to insertion sort, which actually performs very well on small array sizes. All right, so that's a detail that you may want to consider when you go to program this. Unfortunately, this naive strategy of simply just dividing it and conquering it is not going to give you what you want. First of all, there's a problem. All right, so let's take the following scenario. And suppose this is our dividing line. Right, this is the medium. This is not the y-axis. This is just the dividing line where I divided it into left and right partitions. Okay. And again, suppose that we have these 2 points over here that have delta 1 and these 2 points over here that have a distance of delta 2. Right? Simply just taking the minimum, right, say that this is the minimum, is not going to give you necessarily the closest pair of points in the entire set of points. Because we have made this this partition here, we have ignored possibilities that straddle that that dividing point. For example, there could be a point here and a point here very close to our dividing line here, with a distance that is less than both delta 1 or delta 2. Right? So we do have to. We can't simply just partition it and then say, well, that's good enough. We also have to consider, well, what about points that might have been over here in the left partition and a point that might have been over here in the right partition? So here's my first attempt at fixing that. Okay, so our outline is as before, right? We divide it into two pairs. Instead of let me just bullet point this. All right, take the min of delta 1 and delta 2, and then consider all point pairs that such that, let me rephrase that, there we go, such that P is going to be in the left partition and Q is going to be in the right partition. So I'm considering P, Q pairs. Okay. If a smaller distance is found, update the min distance, the overall minimum distance. Okay. That strategy will correct the problem, right? Once we found these two minimum over here and these two minimum over here, all I need to do is consider all points that go between one point is over here and one point is over here, and consider all those distances. The problem comes with how many possibilities are there. Remember that we've split this into two, so there are roughly n divided by 2 points over here. There are roughly n divided by 2 points over here. Okay? How many comparisons would we need to make in this recursive strategy right here to make up for our naive mistake of missing out on all these combinations, right? Well, for each point in the first one, you have to consider pairing it up with every point in the second one, right? So here's my point P. I have to consider all these points, Q, Q2, Q3, dot, 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 right? Every single possible point over there. And the number of such pairs is going to be something like this. In fact, let's be a little bit more accurate about it. How many if I've got n divided by 2 elements over here, and I've got n divided by 2 elements over here, then I have to choose 1 in the first one, right? And then choose 1 in the second one. But you can take out all of the duplicates. So you don't have to, if I choose P over here and Q over here, I don't have to then choose Q and then P. So it's going to be roughly half of that or something like that, right? A number of combinations. Actually, we don't. That's already. I think that's already part of it. It doesn't really matter. You can already see what this is going to be. This is going to be n divided by 4, and it's still going to be order n, right? So in other words, this is going to be a linear amount of non-recursive work. Right. Okay, maybe that's okay. All right, let's go ahead and analyze this idea and then bring the master theorem in here to bear. All right. So what I'm going to do is I'm going to define C sub n to be the number of comparisons by the recursive / divide and conquer closest pair algorithm. At least how we've presented it so far. Right? Note that I split it up into 2 partitions, roughly of equal size and divided by 2. So that's going to be 2 calls recursively. The first one is going to be the left partition. The second one is going to be the right partition. And again, we're going to ignore off by 1 errors here where one gets 5 points and the other gets 6 points, right? And plus the non-recursive cost. What non-recursive cost is there here? Well, partitioning, right? That's going to cost us, right? Potentially, right? We have to iterate through all the points with respect to their x coordinates and say that, well, all these points over here, they go into the left partition. All these points over here, they go into the right partition, all right? So we're going to have to, we're already facing a linear amount of work here to partition it up. Okay. And what other kind of work is there, right? So we have to divide it into 2 sets. We call it recursively. That's already taken care of. We take the closest between the 2 points that we've already been given. Well, that's just constant, right? Plus 1 to find the minimum of delta 1, delta 2, right? So we don't even have to write that down. But with this naive approach, what we've already said is, oops, sorry, what did I do? Not n divided by 4, n squared, right? And so it's going to be quadratic. Oh, I can't believe I did that. Quadratic. There we go. N times n divided by 2 is going to be n squared. I completely screwed that up and forgot the 2 there. All right. So let's go ahead and write it correctly over here. N divided by 4, n squared. All right. So altogether, it's going to be something like 2c n divided by 2. And then it's going to be some function, which is going to be order n squared. All right. That's the highest order term right over here. Right. These then end up being lower order terms. So let's go ahead and bring in the master theorem here. A, the number of recursive calls is 2, right there. B, the amount that we cut it down in each time is going to be 1/2, so that's also 2. And then D, oops, not delta, but D, or K, or whatever we were using, that function is going to be bounded by a quadratic, so that ends up being 2. All right. If you look it up, in fact, I can bring it, there we go. Back here, where's the master theorem? There we go. All right. So remember that A is 2, B is 2, and D ends up being 2. So what is the relationship between A versus B to the D? That's 2 versus 2 squared. This is greater than. And so by case 1 of the master theorem, we get that the number of comparisons made by this algorithm is going to be order n to the D. But we've already observed that D is 2. Right. Asymptotically, it's no speed up, right? It's no different. So unfortunately, our clever little way of doing this didn't really buy us anything. We weren't really exploiting the problem that we got into here is, remember, with our backtracking strategy, our divide and conquer, our brute force. One thing that you have to do with algorithms and data structures is you have to find structure, because the structure is what you exploit to make things efficient, right? What structure could we exploit here? We're simply going to use geometry, okay? So do we really have to do every single pair here? If I've got a pair point here, do I really have to compare it to all the other points over here? Right? If I had a point way over here and a point way over here, do I really need to consider that distance when I know that the minimum distance that I've already found is much smaller than that? No. How can we exploit that? I don't have to consider every single point. I only have to consider points that might be a distance closer than delta. Right? So let's go ahead and draw our depiction here again. Oops. Let's do it this way. Okay. And there we go. There is our dividing line, M. Right? And I'm not even going to write the x and y axis. Let's just say that these are our two minimum distance points, delta. That's the minimum in L and R. L is over here and R is over here. Okay? And there was a minimum pair of points over here, delta 2, but it turns out that a delta 1 was even, those 2 points were closer than these 2 points over here. So we can go ahead and discount those points immediately. Right? And we're focusing on this. If that's not true, then just take this picture and flip it around, right? Okay. Now, what we did before was we considered all possible points in the left partition, and then we, naively looked at all the other points over there. Right? We don't have to do that. Right? Remember that this is a minimum distance of delta. Any point that is going to be over here must be within a distance within delta distance from this point, or less if we're going to find a closer pair of points. Right? So we don't have to consider points way over here. We only have to consider points within a radius, because it's Euclidean distance, of delta from this point over here. Right? How many such points are there? So I'm going to draw this arbitrarily close to my my M over here. Actually, what I'm going to do is I'm going to present this as it usually is presented, and I'll tell you why I think it's wrong, and then I'll tell you why it was done this way. But in any case, suppose that this point is actually really, really, really close to the line, such that it's basically virtually on the line. Right? I only have to search a delta distance away in the x direction and a distance delta away in the y direction, but in both directions, delta and delta. Well, if I draw a bounding box around this thing and I try to pack as many points into it as I can, then naively it's just going to be this point, this point, this point, and this point, and maybe another point in here somewhere or whatever. But in any case, what you can do is you can say that there are at most 6 points in R that may be a distance less than delta from X, or let me call it P, because that's we're doing points here, right? This is point P. Okay, these were the other points A and B, right? Just to give those labels. All right. And that's the way that it's usually presented. And I've never liked that, because if you're talking about Euclidean distance, right, it's actually fewer. All you have to do is draw a radius line of delta up and a radius line of delta down, and then draw a circle around it. Right? there's no way that you're fitting 6 points in there. You're fitting at most 3 or 4. And I've never done the formal analysis, on geometry wise, geometrically wise, of how many points can you pack into a semicircle of a radius delta that are less than delta away, right? Because if you have the argument here is, suppose that you do have 2 points that are less than delta away, right? So you have 2 really, really close points over here, right? Let me go ahead and zoom in on that. You have 2 points that are really, really close. Guess what? That distance, delta prime, would have been less than delta D. You would have found those when you recursed on the right partition to begin with. So that can't happen. They must be a distance greater than delta away from each other, or you would have found them when you recursed on the right-hand side. So how many points can you fit into a semicircle of radius delta that are at least delta away from each other, right? And it's not that many. Of course, you can pack a lot of very, very close points in here, but you can't pack a lot of very, very close points that are at most, or at least a distance delta away, right? So I'd say that there are at most 3 or 4 that you can pack in here, probably at the edges here, up here and here, right? So that there are probably at most, 4 or 3 or whatever careful analysis you can come up with. The point being, let me go ahead and erase this. The point being is that the following observation: for each point P in L, only a constant number of points in R must be examined. Right? That greatly improves our analysis over here. This naive way of doing it goes away entirely, right? Let's go ahead and do that over again, and with the full analysis here. C sub n is going to be 2 recursive calls on sets or arrays, whatever, of roughly half that are roughly half as big as the original. Okay. Yes. Sorry. We do have a comment online here. Oops. We do have a comment online here that did correct me. Thank you for that. Yeah, it's divided. It was order n squared. Sorry, but I didn't see that until just now. Yep. All right. So back to this. At hand, there's 2 recursive calls on arrays that are roughly 1/2. We still have to partition it. We still have to, given this distance and this distance over here, we still have to find those. But now we don't have to do this naive every pair of points that cross the lines, right? So plus n for the partitioning, plus 1 for the finding min, and plus now it's only, if you, depending on which one of these you consider the very, very loose analysis, the tighter analysis, or maybe the more advanced geometric analysis of 3, right? Whatever that constant is, it's just c times n. In other words, it's going to be 2 cn divided by 2 plus some constant cn plus 1, right? Who cares what this constant is? C plus 1, all right? It doesn't matter, because when you look at the master theorem again now, it's still going to be, A is still going to be 2 recursive calls. B is still going to be 2 because you half the input every single time. But now D is only order n. It's linear. So now D is 1. So A versus B to the D in this case is going to be 2 is equal to 2 to the first. By case 2 of the master theorem, we now have that it's order n to the D log n, which is going to be C sub n is order n to the D. D is only 1, so I won't write that. Log n. Right? polylogarithmic, right? Or in this case, it's quasi-linear, right? That is a huge speed up. Whereas it took us, 2 minutes before on something that's of 10,000. Now the speed up is only going to be a factor of 10 instead of 100. So we could actually get that done in about 10 seconds instead of the 1 second that it took before. Instead of taking days or weeks or months to do points of size 1 million, it'll only take us a few seconds, right? That is a huge speed up. That's just as good as sorting, which is what we're going to end up having to do as part of a subroutine to this thing, okay? So very, very good algorithm, very, very good way of dividing and conquering it. The devil is in the details. I think that this is the first time that I've ever actually assigned it as an exercise to program. So I did want to go into a little bit more detail on what you will need. Okay. To do that, I'm going to go back over to our notes here, and let's go ahead and outline. I'm not going to do full pseudocode here, but let's do an outline of what you would need to do. Right. So outline of the good recursive divide and conquer closest pair algorithm. All right. So as a step 0, I like to start at 0. Here's our base case. Right? If let's identify the input here first. The input is going to be a set of points S, pre-sorted with respect to the x coordinate. So pre-sorting this is rather easy. All you have to do is, given all these points, sort them with respect to x. That will make the partitioning easier. If it's already pre-sorted with respect to x, then all we have to do is, well, there are 10 elements over here, 10 elements over here. Just take the middle index, m divided by 2, floor, ceiling, depending on your programming language, or rely on integer truncation. That's going to make the partitioning easy, as well as a couple of other things that we're going to do. The base case here is if the size of S is small enough. Use brute force, that is, generate all pairs to solve the problem, right? And return the pair / distance of the minimum distance pair, right? Again, that cutoff could be, let me do it like this. That cutoff could be 2 points. That's the naive case. If you get down to 100 points, especially if we're when you actually program this, we will be testing it against 1 million, 10 million, a billion points or whatever. Recursing after a certain point, it doesn't pay off anymore. So you can actually set that and tune that as a variable. That's what I did. That I set a variable of x or whatever, whatever variable name you can come up with. Again, naming things is hard. And what if the input is less than or equal to that? I switch over to the brute force algorithm and simply report that as my solution. Right. And then by putting that into a variable, you can, of course, tune that. Okay, well, 1,000. Kick that up to 1,500 or something like that. And then you'll start to notice that, well, if you kick it up to 10,000, it ain't going to run very, very quickly, right? So you can fine-tune that and play around with that in your actual implementation. Otherwise, partition S into 2 roughly equally sized arrays or lists or whatever, L and R. And note that if you've already pre-sorted, again, this is easy. All you have to do is the indices run from, say, 0 to n minus 1. Just take n, the size, divided by 2, and that gives you roughly the middle point there. Not only that, but you with random access, you can jump to that. And because it is sorted already in as x, When you split it out into two, this one is sorted with respect to x, and this one is sorted already with respect to x. So you don't have to resort them at all, and that's really, really convenient. Recursively, find the two closest points P, Q in L, and I'll give them another name, R, S in R. Okay? Then you choose the minimum among those. Choose the closest pair between P, Q and RS. Call it PQ just for convenience here, right? If it was actually RS, all right, fine, then that becomes your PQ with distance delta. Hopefully this works. Yep, distance delta. Good. All right, then what you need to do is this trick that we just described. For each point over here in the left partition, you need to compare it to points over here in the right partition, but you need to make sure that you're not doing them all. If you end up doing them all, then that degrades into an order n squared algorithm. You need to make sure that you're only looking at it within a slice, basically. And what do I mean by that? Let's go ahead and go back to the diagrams here. So we're going to only consider one x over here, right? The slice that I'm talking about here is, here's the median point here. This is where you partitioned it up all to begin with. And by the way, how do you do that? Well, you find the median, right? Of the point over here closest to this and the point over here closest to this. Then you can take the median or the average between those 2 points. Oops, didn't want to do that. There we go. And you can do that efficiently because, again, you have random access. You can jump to the midpoint, and once you've split it out, you've got these 2 points. You know that those are the two closest to your partition. Just find the x value that divides those two evenly. Okay. All right. So for each x, we only have to consider the following slice, right? That here's L over here, right? And here, I don't know, here's the x-axis. It doesn't matter where it is. But this is going to be a delta distance away, right? All these other points over here, you can immediately throw those out, right? So how are we going to do that? Well, remember L was already sorted with respect to x, right? So all we need to do is jump to the, there could be a whole bunch of points in here. All we need to do is jump to the point in the partition that is delta distance away, and we can do that using binary search. Here's the idea. You jump into the middle and you determine, is that within delta, all right? Nope. All right, well, then we'll jump into the middle. We've cut it in half effectively. Jump into this half. And if the points happen to be tightly compacted over in this area, then that would be where, if you cut it in half, it's within delta, so we need to go that way to find the break-even point. The break-even point, excuse me. So all you need to do is use binary search to limit the L to a slice that only contains points a distance delta, right, with respect to the x coordinate, of course, from M, right? In other words, you're looking at a slice from M up to M plus delta. That's this slice right here, right? And you can do that really efficiently because, one, L is already sorted, and so you can exploit binary search to find that cutoff point right there. Okay? All right. Back to our notes here. Uh, let's see. Find choose the so part step one. Find the median x between the two sets. All right. And then finally, then next, build a subset of S whose x values are in. Actually, what you can do is you can do it on both sides. I just illustrated it for one side, so you can do it for both sides. All you have to do is go m minus delta for the other side, and then m plus delta for the right side, right? I was calling it L. I shouldn't have called it L. I should have called it R. Hopefully that's clear, though. Let me go ahead and go back and relabel that, right? So this is not the L partition. It's all sorted with respect to L to S. That was my mistake. So here's R. It's already sorted with respect to X. Use binary search. We're also, doing the same thing on the other side. Delta away, right? So I'm limiting it to the left slice, whereas this is the left partition, all of the points over here. If I only consider points that are delta away from the median, then I'm going to call that the left slice. And over here, this is the R slice. Why do I limit it on both? Well, I don't need to consider a point over here that's further distance away from delta, and then consider even if I have a point over here that's within that slice, I don't have to compare those two. I can limit it on both sides here and really cut down on the amount of work in practice. Okay, you could of course get away with doing every single point over here as long as you're only comparing it within the slice over here, and that would still get you the asymptotic behavior that we already analyzed. But there's no reason to do that in practice. Any points that are closer than delta away are going to one of them is going to lie in this slice, the other one is going to lie in this slice. All right. So build a subset of X whose values are in this. And you can use binary search on both ends. Binary search to find the slice cutoff over here. Binary search to find the slice cutoff over here. And now you can ignore everything else outside of those two things. You've built a subset, all right? Potential problem here. All right, well, here, let me go ahead and put in, you need to use binary search to find these slice cutoffs. All right. Using a linear search gives you order n behavior and overall a quadratic algorithm. All right. Oh, sorry. I was looking at my notes here. And here's another tip that I found when I programmed this. Let me see if I can do this. Yeah. Make sure you include all points that may have equal x values. Right? So what I mean by that is you could use binary search to find that cutoff. Say that the cutoff is 5. Right? But there are other points over here, above and below it, with the same x value, but different y values. So you need to make sure that you include all of those. What that means is you may need to, once you find your cutoff point over here, you may need to use a little bit of linear search to continue and grab all points with an with an equal y value going up and down here. Excuse me. When I say going right, I mean right in the array, in the array sense. Here's that point that gives you that cutoff. Look at the next point, the next point, the next point, as long as the x value is equal to it. Once that x value becomes larger, you know that it's outside of that slice range. Okay. Another tip here: you may you may want to maintain a separate left and right slice. Right? Don't just throw them all in. Right. You could take the entire set S. And then winnow it down to the left and the right slice. but it is going to be helpful to keep those slices separate. And so what you're going to want to do is you're going to want to find the cutoff point in the left partition and then the cutoff point in the right partition, and keep those two things separate, just for convenience, basically. You'll see here in a moment when we continue the algorithm. Right? So 6. For each x, or p, I'll say, in the left slice, compute the distance to each potential point in the right slice. If you find a closer pair, update the closest pair / distance. Right? That's what you're going to ultimately return from your recursion. Right? Again, you have to be careful. You can't just do it all for every single point on the right, nor can you be lazy about it and just look at every point in the right slice. What do I mean by that? Let's go ahead and go back to our diagram here. I'm going to repeat that. Let's go ahead and create our midpoint here. And suppose we've got our left slice over here, our right slice over here. This is L, this is R, this is the left slice, and this is the right slice, right? And suppose that we've got a point P over here that we then need to compute things in the right slice, okay? If I did every single point in the right slice, you got to be careful. It could be that every single point in the right partition lies within this slice. It's just that they're very, very far away as far as their y coordinates are concerned. So you can't just go naively and for a point P over here for each point in the right slice, right? This is wrong. Given P in the left slice, for each Q in the right slice, there could be order, do your work here. There could be an order n number of points in this. They could all lie up here, and it could be a very, very unlucky kind of input. So you have to be careful. You can't do this. Right? How do you do this instead? Same trick as before. If I've got a P here, right, I only need to look at for each Q in the right slice, whose y coordinate lies in a horizontal slice, in p dot x, or sorry, p dot y minus delta, and p dot y plus delta. What does that look like? I'm going to switch colors here. Here's P. It has values x and y. So I'm looking at its y value right here. Okay. And now I only need to look at things in the right slice that are delta distance up, right? And delta distance down. I've already limited myself to the right slice here by building that slice. But now what I need to do is I need to find this point, the index in the array with this point, and the index in the array with this point. Right? This immediately presents a problem, because how do I do that efficiently? Remember that L and R, which is all the points here, they were sorted with respect to y, right? Or sorry, what am I saying? They were sorted with respect to x, not y. What I need to do in order to do this efficiently is I need to do a binary search for this range on the right-hand slice with respect to the y coordinate. There's no way that I can do binary search if it's not already sorted. So, step A, sort R sub s with respect to the y coordinate. and in fact, sort a copy of, because we may want to maintain that the ordering with respect to x. Okay, so sort a copy of rs with respect to the y coordinate. When we do that, then we can exploit binary search to limit the number of comparisons, number of distance calculations that we have to do. That's for each point, right? So once we get to another point here, then we have to redo our binary search to find its region right here, right? But we don't have to resort it, right? We don't have to resort it for every single point over here. If we just take the copy of this RS over here and we sort it with respect to Y, then we can repeatedly do binary search on it over and over and over again. Okay, that's my proposed solution. We'll talk about whether or not it is a good solution here in a second. It's certainly a better solution, but so careful. Right? There may be order n points in the right slice, even if so. Yeah, I'll just leave it like that. Right. So solution A, which is what I just talked about. Sort the right slice with respect to y, their y coordinates, and use binary search to limit the number of comparisons to the range of we've called it p.y minus delta. Let me LaTeX that. Up to p.y plus delta. Right. And here I'm taking the point's y coordinate there. Okay. The y range. There we go. All right. That will work, and it will actually give you an efficient algorithm. But before we commit to that, let's actually analyze it. Okay, and let's go back over here. All right. So remember, we had this recurrence relation for the improved version here, where we had to partition it. We had to take the minimum, and then we said, well, you only have to, for each point over here, you only have to do a constant number of comparisons over here. Since there are roughly n divided by 2 points over here, then that's going to be some, order n, right? So what is it going to be now that we are committing to doing additional non-recursive work? We still have the same recurrence before, 2 recursive calls on arrays or sets or lists, roughly 1/2. We have to partition. But remember that we pre-sorted everything, right? We pre-sorted it, so we don't actually have to we can find that, and then we can cut it in half or whatever. We can maintain those indices. We don't have to go through and say, all right, you belong on that side, you belong on that side, you belong on that side. So I'm immediately going to get rid of this, right? Just because you really don't have to do it. +1, all right, that's for the determining the minimum delta, plus our non-recursive cost for making all those comparisons. Now again, 6n, or that could be 3 as low as 3n, right? Whatever. This is for comparing points across the midpoint. Right. But now we've introduced additional work here. In order to make that efficient, we have to sort the list, sort a list of size order n, right, by their y coordinates. Right. So in other words, we'll just bring the best sorting algorithm that we know to bear. Merge sort, quick sort, tim sort, whatever. That's going to be order n log n, right? At that point, we can go ahead and ignore these 2 lower order terms. This is going to be 2 Cn divided by 2 plus n log n. Now you have to be careful here. A and B are the same, right, with respect to the master theorem. But what is D now? Right? Is D 1 as it was before? Is n log n, is that bounded by order n? Nope. We've got a logarithmic term up here. If we go just slightly more, 0.000001, then that would be true, right? That n log n would be bounded above by anything larger than a linear, because of course this lower order term log here would eventually disappear, and this term, even if it's super small, would dominate, right? That would be true, but that's still left not all that satisfying, right? And it makes this comparison over here with a versus b to the d hard, right? In fact, it's going to end up being strictly greater than, which gives us, where's the master theorem here? Which gets us right back to here. And it's going to be order n to the 1.00001 or something like that, right? And I mean, you can do that kind of naive analysis because again, big O analysis is very loose, right? This is very this is true, right? I just bumped it up a very little amount. You can always bump it up a little amount that's even littler, right? So add 50 more zeros in there, right? And it would still be true. Right? So it would be a very loose analysis. Fortunately, there is a fourth condition of the master theorem. If you got the book Leviton, I believe it's in there. It might be in CLRS as well. I'm not sure. But there is another fourth condition of the master theorem that involves logarithmic terms here. And basically what it comes out to is that C sub n, at least as we presented it for now, is going to be order n to the log, or n log, but log is going to be squared here. There's an additional logarithmic term. That's going to be better than any n to the d, where d is strictly greater than 1. So this a much tighter analysis would give you something like this. Now that's not as good as the ideal of n log n. But it's going to be good enough for your programming assignment. That if you do it as I've just outlined here, that's the way I did it initially, at least, to make sure that it actually worked. It worked as in like our billion or so size test cases would actually execute on the CSE server in a reasonable amount of time. But ensuring that if you use the naive approach from the beginning, the order n squared algorithm, no way, that's going to take weeks. So this is good enough. Right? How can we actually improve to an actual order n log n? Right? And unfortunately, a lot of presentations don't go into this. What I had to do is I had to go back to the original paper from the 70s or something like that to find out what did they do to actually achieve order n log n. I think it's also in CLRS if you've got that book. But when I went back there, I also found out why they have this very loose analysis of you go over delta value, and you have 6 points instead of, well, if you're using Euclidean distance, draw a circle and there are even fewer points. Why are you presenting it like that? And it's because the original paper presented it like that. Because the original paper was using a more abstract notion of distance. The norms, the paper was said, okay, well, we'll present it as the L0 norm, which is the Manhattan distance, which is why they actually drew it as a rectangle instead of a circle around it. When I went through and read that paper, I found how they actually achieved n log n. And basically what they did is they pre-sorted two lists. They pre-sorted everything with respect to x, and they pre-sorted everything with respect to y. And when they built their slices, they made sure that they only built a small subset using a combination of binary search and basically what I termed as like a kind of a reverse merge sort, where you go through and you only select out that which you care about. So everything is sorted, you can go ahead and jump to the location where you want, jump to the location you want, and just take that sub list, or that sub slice, and create a new list there. That required, when I programmed that version, that required passing in a lot more. Not only did you have to partition left and right, but you had to pass in a set that was, or a list that was sorted with respect to X, and a list that was sorted with respect to Y. And then when you handed it off, and you only took one partition, you had to make sure that you only included those relevant points in the Y version of the list. So it involved a hell of a lot much more work. It was still correct, and I got it, and I achieved that order, that theoretically best order n log n, because you do have to ultimately pre-sort everything, and so you've already resigned yourself to n log n here. But I found that in practice it was actually slower because of the additional work that I was doing. Just like we talked about yesterday with respect to Karaksuba multiplication and Strawson's matrix multiplication, asymptotically, yes, they're faster. But in practice, they're not, because of all this extra non-recursive work that you're doing. It only pays off when there are very large matrices or very large numbers in those two instances. And in this case, it probably only pays off if you've got a very, very large set of points. I'm talking, and I never found the crossover point, so I gave up. We're talking way more than several billions of points. So my suggestion is to go with the solution that I've presented here, where you pay for the extra price of resorting with respect to the Y coordinate on every recursive call. Right? But again, the B solution here is much more complicated. Right? It requires sorting and avoid resorting by. How did I write it here? Avoid resorting by sorting once at the beginning with respect to the Y coordinates, and you maintain two lists. Here's all the points with respect to X sorted in with respect to X. Here's another set of the same points but sorted with respect to Y, and then you can make those splits much more efficiently, at least asymptotically, reaching that order n log n rather than n log squared n. But logarithmic terms are so small that it really doesn't matter. And sorting algorithms, at least the built-in sorting algorithms, are so good that you're never going to notice the difference. You will notice the difference between n squared and n log squared n. All right, so you will need to have an efficient solution for your assignment to actually get it to work. All right. Okay. So with only about 20 minutes left here, what I wanted to do is I wanted to get into the next kind of part. I will note here that at this point traditionally, I've assigned other exercises, including Gaussian elimination, which is kind of a divide and conquer approach to solving systems of linear equations. I've also talked about more generally linear optimization problems. We might come back around to those. I usually cover them with respect to divide and conquer, just because they involve matrices and so they're a nice companion to Strawson's. They're not necessarily divide and conquer kind of approaches, but you can kind of see how they might be divide and conquer. But in any case, I have not assigned those as exercises this summer. So I'm going to put them as a lower priority of coverage, and we might come back around to them if we have time later this week. But what I wanted to do is I wanted to make sure that we covered everything by tomorrow, by Wednesday, that you need for your assignment 2. You have 4 programming exercises. 3 of them have already been covered. We're going to cover the 4th one today and probably bleed into tomorrow. All right? And I'll just use the same note set here. It's Huffman Coding. You might have heard or seen of this before. You're going to actually program it now. But before we get into that, what we need to do is we need to talk about coding theory in general. When I was a grad student, I loved coding theory. I never did any research in it, but I took as many coding theory courses as I could. Coding theory, not as in code, like how do you code, how do you program Java, or how do you program Python or something like that. Coding theory has two branches. The first one is where you add redundancy to a signal to ensure that information is not lost in a noisy channel. Right? And so what do I mean by that? And here's the naive way of thinking about it. Right? So the simplest way is, suppose that you're sending a bit, right? As a single zero over a noisy channel. A channel in which information can be lost. Here's the scenario: you have you have your wireless computer of 802.11g or whatever it is, and then you stick in your microwave burrito, which is has microwave radiation, which is near or at the same frequency as your computer, and you lose your internet connection, right? Or everything becomes slow because of the noise. For wireless connections, that's background, radiation. That's interference. For a physical channel, it could be, perturbations in the electrical signal, or something like that. If you're physically yelling at somebody, right, over a crowd, the crowd is the noise. They're not going to be able to hear you. So there's a chance that your bit gets flipped to 1 when you receive it, right? And that's not good, right? Now you're getting the wrong information. You're getting corrupted files if this happens too often. Hopefully the noisy channel has a certain probability of flipping a bit. Right? Now, if that probability is very, very high, 99%, that's actually not a noisy channel. The noise is actually helping you, because if you receive a 1 with a 99% probability, they probably sent a 0. So just go ahead and flip whatever you sent, right? Instead, the noisiest channel is if it's a 50% probability that a bit gets flipped. Now you have no assurance about any of the data that comes through at all. Zeros could be randomly flipped to ones. Ones could be randomly flipped to zeros, right? You hope that the probability is very, very low, say 0.0001 or something like that. And that a 0 becomes a 1, that a 1 becomes a 0. So for the most part, you can send through thousands and thousands of bits, but every 10,000th bit is going to get randomly flipped. You want to be able to either correct that or at the very least detect that, right? So here's the easy way of doing it. If I want to send a 0, instead, I'll just go ahead and send 2 zeros, right, over the noisy channel. And if the probability that 1 bit gets flipped is very, very low, right, then say that I receive 0, 1, right, or 1, 0 instead of 0, 0. I now know, that's not any part of the encoding that I know of. One of these got flipped. Was it the first one or was it the second one? I don't know, right? But that gives me an opportunity to say, I've detected noise. And I can say, all right, send that again, right? If you're yelling over a crowd, you can say, I didn't quite get that. Go ahead and send that again. Or in a network, you can say, I lost that packet. I lost that bit. Send it again, right? And the probability that the same exact error occurs is actually really, really low, right? Well, if you receive 0, 0, well, then it must have been a 0. If you receive 1, 1, then it must have been a 1. It's possible that if you receive a 0, 0, that they actually sent a 1. But the probability of that is extremely low. It's going to end up being p squared, right? Which is even lower, 0, 0, 0, 0, 0, 0, 1. 1 in 10 million instead, or something like that, right? I always get confused with decimal points, so don't quote me. But in any case, the probability is extremely low because both bits get flipped, right? The probability that the first bit gets flipped is this, compounded with the probability that the second bit gets flipped is this. Now that is assuming that that this probability is independent of each other. In practice, that's not necessarily the case, because if you've got a loud bursty noise, it's more than likely that that noise is going to corrupt more than one bit. But you get the idea. The cost, however, is twice as many bits. All right. Well, if I want even better detection and correction, I could say send 3 bits. And now if I receive, say, 001, then with high probability, it was probably this bit that got flipped. So I don't even have to request that they send me, resend it to me. I'll just go ahead and assume that it was 000. Right? Now the probability, because you're sending 3 bits, the probability is even lower, p cubed or something like that, that everything got flipped. If I just send more and more bits, right, then I can arbitrarily decrease this probability to whatever I want. The problem, of course, is that I'm sending more bits. And something where I had, an internet connection of 10 megabits per second, if half of that throughput, if half of that bandwidth is being taken up with extra bits, with an extra bit of information, then effectively now my 10 megabit connection is only 5 megabits, because that's as much data, actual data, that I can shove through the network connection. So that branch of coding theory involves, how do we only add a little bit more information, a logarithmic additional amount of information, in order to both detect and or correct errors in transmission or even in storage. CDs, for example. You may not be of a generation anymore that has CDs, but you can scratch up a CD pretty bad and it'll still play, because it uses something called Reed-Solomon encoding, where it's okay if a few bits get flipped, because in the decoding, it can actually detect and correct those errors. Only if you really, really scratch it up and have too many errors is the code not able to recover from that. That's one branch. And if you're really interested in that kind of stuff, I would highly suggest that you take a coding theory course over in the math department. They have several, like 2 or 3 dedicated researchers to coding theory. And you can always see, announcements on over in the math department on graduate theses on coding theory, and you can really get into it. The other branch is something that you're really familiar with, is compression. Right? Here, what we want to do is we want to remove or reduce information for efficient storage. Right? Zip files, right? Examples. Zip files. JPEGs, MP4s, MP3s, etc. Right? Now, zip files, those are going to be what is called lossless. Right? In other words, when you take your bank information or your spreadsheet or something like that, and you zip it up. By the way, Excel sheets are already zip files, so are Word files. They just don't call them that, and when it opens up in Word, it decompresses it. So if you're ever wanting to actually take a look at the binary representation of one of those Office files, you'll find that they've already been zipped up, they've already been compressed. But you want them to be lossy. Imagine that you compressed your 5-paragraph essay for English class, and it started losing sentences, or it started losing letters, and then you decompressed it and handed it in. That's not going to work. So zip files generally are lossless. In other words, when you decompress them, all the same information should still be there. However, these other formats, JPEGs, MP4s, MP3s, these are what are called lossy. Right? And usually you can tune that lossiness. If you have greater compression on a JPEG, it'll look a lot more, digitized. It'll look a lot more pixelated. It's potato quality basically. But it's more and more compression. You can take several megabytes of an image, compress it down to a few K, a few tens of thousands or 100K, getting like a factor of 20 or 30 or better compression, because it is actually throwing out information. It's only it's coming up with a way to approximate that original image with a little amount of information, rather than storing every single bit and RGB value of that original image. MP4s and MP3s do the same thing. They take out also redundant information. So with an MP4, if you've got a video image where one frame does not change to the next frame, it's not going to store both of those frames. It's only going to store the difference between both of those frames. And if there's no difference, then it stores one frame and says, play that for 5 seconds, like I do at the beginning of my videos on YouTube here when I play some music. The actual video doesn't change at all. So those are really easy to broadcast, and there's no lossiness at all. And you'll see this with artifacting a lot, that you're playing a video and then something screws up and you see a ghost of the image, right? And that's because something went wrong or corruption in either in the encoding or in the decoding or something, and that ghost image remains, right? As somebody's the image changes, and so that somebody's moving, but the original image is still over them. You can't see their face. You see the original image, and then it looks kind of weird. Really cool effects, but that's a result of it being lossy and having keyframes where it resets and now we're going to store the entire frame, and now we're going to for a time we're only going to store the differences from that frame on. Those are lossy versions. What we're going to look at is Huffman Coding. It's a lossless, mostly used on text compression algorithm. And basically the idea here is that common characters, right, are encoded with shorter code words, and rarer characters are encoded with longer code words. Right? This is what's called a variable length encoding scheme. Right? So the idea here, and this is where we'll end it today, and we'll get into the details tomorrow, but the idea here is, think about the English language. If you've ever seen Wheel of Fortune, if you're trying to solve a puzzle, a word puzzle, and they give you the opportunity to choose some words to reveal, or some letters to reveal, do you immediately choose XYZ? Those are the least common characters in the English language. Yes, there are words that use those things, but the more common characters, RSTLE, right? You're going to choose those first to reveal as many letters as possible. So with an encoding scheme like ASCII, every single letter is represented by, well, technically 7, but we'll go ahead and go with the normal 8 bits, right? Z is 8 bits. A is 8 bits. Why do it like that? That means that that's a fixed block encoding scheme where everything takes the same amount of information. Whereas in a typical English book or something like that, Z is going to be a lot less common than R. So why don't we encode R with just 1 bit? And then we'll say that Z is encoded not by 8 bits, but by 16 bits or something like that. And that way, the more common letter, R, it only, anytime you see a 0, that's R, that's R, that's R, that's R, that's R. There's only 1 bit of information to encode that. And because it's so much more common, that means that the average number of bits required to represent that text is going to be much smaller. Yes, you're paying more bits for the Z, but that's so infrequent that it doesn't matter, right? The cost is minimal. Whereas the cost savings over here to encode a common letter with a shorter bit string is far exceeds the blow up cost of representing Z. You can typically get at least a 15 to 20% up to 60% compression ratio with this kind of scheme based on actual English stuff. Like if you just took some random letters or something, random information is actually not compressible. DNA sequences, for example, are more or less kind of random. There's a normal distribution, I should say. At least that's my understanding. Any biologists out there, please correct me. There's a normal distribution between the four codons, the AGCTs, and so trying to compress a DNA string is actually going to be kind of difficult because it's random data. Truly random data cannot be compressed at all. Only data that has, again, structure, we call that entropy in coding theory, it can be highly compressed. The more structure it has, the more that you can compress it. Okay? I don't see any other questions, so that's where I'll end it today, and we'll pick up with Huffman Coding tomorrow.